Information processing is an important component of learning and memory. In fact, if new information isn't processed, it won't lead to permanent new memories, and learning will simply not occur. On the other hand, the more extensively new information is processed, the better it'll be remembered. The steps involved in the import and processing of new information is summarized in what we refer to as the information processing model.
What happened?
Hi, I'm Keith Werner, founder of LabLearner. I'd like to talk to you about the information processing model. This is a very important model in understanding how children learn. It's also important because we used it as the basis of the design of our LabLearner program. Let's consider this model. In essence, the input arrow indicates new information entering the brain. Now, most information that we are presented with never makes it to the learning pathway and is lost. This is indicated by the downward arrow on the left, leading to forgotten. We constantly receive an enormous amount of information, literally thousands of stimuli per second. And we can't process all this information at one time. Consider, just for an example, the feel of your right foot at the very moment that I'm speaking. Now, in all likelihood, you weren't thinking about your right foot at all until I brought it up. However, now that you're thinking about it, you can sense it, and you can sense information being sent from it to your brain. For example, its position relative to the rest of your body. Obviously, it would be very difficult to concentrate on anything else if we spent all of our time with information coming from our right foot, let alone the rest of our body and all of the environment. New information that does enter the brain is available temporarily in working or short-term memory, where it may either be further processed into long-term memory or lost and forgotten. This is indicated by the second arrow leading to forgotten. Information is not stored in short-term memory for very long, as the name implies, perhaps only a few seconds or minutes. It's either processed or lost forever. Not only is the storage of information in short-term memory brief, but it's also very limited in capacity. We can only place a few bits of new information into short-term memory before it's filled, and new information begins to replace previously stored information. Somewhat like when we overfill a glass of water. This is essentially what happens when we're trying to memorize a telephone number, for example, and someone comes up and talks to us, and we completely forget the number. Essentially, we're replacing the number in our short-term memory with the new information that the person has given us. The conversion of new information from short-term memory to long-term memory requires a very important process, and this process is called consolidation. As suggested by the information processing model, consolidation is a complex process involving the comparison of new information in short-term memory with previous knowledge through the retrieval of related information from long-term memory. Virtually no new information is consolidated without first comparing it to information that we already have. When thinking of short-term and long-term memory, sometimes it's convenient to consider the analogy of a university library. When we first enter the library, we come to the periodical room. And this is a room where we have the most recent issues of periodicals, magazines, and newspapers that are readily available to anyone who wants to use them. However, they're not stored in the periodical room very long. This is analogous to short-term memory. Long-term memory, on the other hand, is more like the stacks of the library, the countless floors and rows of old journals and books, journals that are bound together, organized in some fashion, date, chronological order, alphabetical order, and are stored for long-term reference. Not only is there a tremendous amount of information, but this information can be very old indeed. And very much like the old stacks in the library, every now and then we come across a memory from our long-term memory that we've just completely forgotten that we even knew. Events, even faces that we haven't thought of for years. And what about the transfer of information from short-term to long-term memory? Does the library analogy still hold? How can we consider consolidation? Well, in any library, the way that information or periodicals are moved from the reading room where they're on short-term display to the long-term display of the stacks is by a librarian. And so, in our analogy, the librarian represents consolidation. Next, let's talk about retrieval. Every bit of new information will be compared to old information already stored in long-term memory banks. Retrieval, in the library analogy, is pretty straightforward. It's represented by the card catalog in the old days or the computer terminal today. Let's consider retrieval in more detail. It should be clear by now that no new information will enter our brain without being compared to information that we already have stored in our long-term memory. Let's do an experiment to demonstrate this. I'm going to look at this photograph and I'm going to describe it to you. You'll have your eyes closed and paint a visual image of the scene that I'm describing. Okay? So now close your eyes and we'll get started. The scene is of a room, and the room is early American in its design and in its feel. It has blue plank walls and a white painted plank ceiling and natural hardwood floors. There's a writing desk with a green tablecloth on it with candlesticks and papers. There's a small side writing desk to the side of the room against one of the walls, and over it is a painting of a sailing ship. Along two of the walls, there's a total of 3 French windows that allow light to flood into the room. Now this is the actual picture that I was looking at. Now think about how different it is from what you imagined. It couldn't be anything other than different because you imagined the room with plank windows and tables from your own experience. You can't control this. All new information is encountered in terms of previous knowledge. Subsequent rehearsal of the new information in the context of what we already know may then lead through consolidation to its permanent storage in long-term memory. Rehearsal comes in many forms in the classroom. Homework problems that necessitate application of information gained in class is rehearsal. One student explaining new information to another is rehearsal for both students. Or students working on their lab report based on data that they collected while conducting an experiment
is rehearsal as well, and so on. Actually, virtually any time a student refers back to newly introduced information and uses it in any way, rehearsal takes place. And it will help them to consolidate the new information into long-term memory. By far, most information in short-term memory never makes it to long-term memory. It is not consolidated. It is lost and forgotten. In the information processing model, this is represented by the third arrow that leads to forgotten. For information to remain in long-term memory, new connections between nerve cells in the brain, or neurons, have to be made. This process is a physical change that involves the turning on of genes and making proteins.
Learning is a physiological process. And like any other physiological process, it's going to be affected by the overall status of our body. Things like sleep, nutrition, exercise, or drugs will have a big effect on how we learn.
Viewed from this perspective, we see that learning isn't magic. It's science, it's biology. Also from this perspective, we can see that as educators, we literally mold, physically shape the brain of our students as we teach them. This single fact is enough to encourage the blend of neuroscience with classroom practice so that we can help control this complex process to help our students learn. As suggested in the information processing model, attention and executive functions play various and controlling roles in the overall process. Let's talk about executive functions. Executive functions essentially oversee the handling of new information. It orchestrates the retrieval of relevant pre-existing information from long-term memory, guiding rehearsal while helping direct attention. When a student decides that a new piece of information is similar to something that they've seen before, that's an example of using their executive functions. When a student is reading and realizes that they didn't understand a concept that they just read in a textbook, for example, and decides to reread the paragraph containing it, they use executive functions both to check their understanding of a concept and to formulate a plan, that is, the rereading of the paragraph, for improving their understanding. As the information processing model suggests, attention is required throughout information processing. No new information can be consolidated into long-term memory if we do not attend to it. Executive functions are involved in helping students decide what they should focus their attention on in any given circumstance. Thus, executive functions oversee and guide almost all areas of information processing and learning.
It should be clear by now that simply inputting information into the brain doesn't necessarily lead to learning. And this is because unless information that we have inputted into our brain is further processed, it's going to be forgotten.
Actually, presentation of new information to students constitutes only the first step in the process of learning. According to the information processing model, I taught them actually means that the new information presented to students by the teacher was processed and consolidated by the students and is permanently available to them in their long-term memory. Even a quick overview of the information processing model presented here suggests two important roles the classroom teacher plays in loading students' brains with essential long-term memories. The first is in selecting and presenting the information for input into short-term memory to initiate the process. This is often done in collaboration with district curriculum specialists. The second role of the teacher is to facilitate consolidation. That is the transfer of information from short-term memory to long-term memory. Since, as we have seen, short-term memory has such a small capacity, we must be sure that only the most essential science information be placed there. If not, students may consolidate trivial facts, while fundamental concepts are lost and forgotten. Simply stated, a major goal of education is to facilitate, through information processing, the accumulation of important memories in the long-term storage of students. A second and equally essential goal is to train students to access selective information from their long-term memory and to use the information to solve problems, find solutions, and create new information on their own. Hands-on science instruction accomplishes both of these major goals. LabLearner uses the information processing model in the design of all of our programs. LabLearner experiments focus students' attention. Meaningful and thought-provoking post-lab analysis prompts students in retrieval and rehearsal tactics.
Even the very sequence of LabLearner curriculum cells is designed to exploit previous knowledge from cells that came before. Therefore, we're allowing the students to consolidate the information and to develop a network of scientific concepts.
And that's why the LabLearner approach to science education has always been referred to as the science of learning.